Hello. My name's Dan Smith. I'm here for Angelos, who couldn't make it today. He's the one who worked on this talk and prepared all the slides. Hopefully I'll do a good job of covering the material he prepared. I'm here to talk about pattern matching and all the associated features that we've been working on the Java language team over the last 6 or 7 or more years. So if you're running on Java 11, none of these features are there. If you're on 17 or 21, incrementally, some of these things have been added. And if you go and download 24 today, you can be right up to the latest here. If you have not played with pattern matching in Java before, I hope this talk gives you a sense of what's there and encourages you to go out and experiment with it. If you have, if you know some of these features, I hope putting it all in one presentation and talking about the connections can help you see the bigger picture, the paradigm of why these features, where are we headed, how do they all work together. So to start, let me take you back to Java 11, or even you could write this code in JavaOne. If you wanted to declare some classes that capture some data and then write a query that works on that data, it might look something like this. There's some class declarations that I've highlighted, really simple. I've left out some of the details here, but you've got a point class, and it just captures an x and a y value. You've got a colored object that wraps some arbitrary object and then attaches a color to it. That's the whole API. Really simple, plain data objects, really flexible. It's one of the reasons people like Java, and one of the things that made it popular is really easy to just declare these things and roll with them. On the use side, if manipulating this data isn't part of the API itself, but as a user of the API, if I need to ask questions about it, it can be a little crafty. So in the subheading there, the goal in this code is to decide if I'm looking at a colored object that is yellow. That's 2 things. Colored object that is yellow, contains a point, and the x value of the point is 1. So 4 different pieces of a test that I want to perform on an arbitrary object. And there's the code to do that. First thing we're going to do is see if we're working with a class, an object of the right type. And if we are, we're going to turn around and perform a cast. So Instanceof is a test that says, is this the thing I'm looking for? And then the cast is just there to make the compiler happy so that I can work with the members of the type colored object. And we repeat that pattern again in a few more lines. I have an object. Is it an instance of a point? If it is, OK, perform a cast. So there's these pairs of Instanceof and cast that you may be familiar with in writing your own code. And it's totally manual. Nothing in the language is going to help you do this right. But it's just a pattern that you might want to follow in order to get to the members of these objects you're working with. Then once you've got the objects, you can invoke accessor methods. Those methods will return different pieces of the data. And we've got some for the colored object, one for the point here. And once I've got all those pieces, I know that the data is in the right shape, and the last step is to look at the data and make sure it meets the values in the data are the right things. Is it yellow? Is it the number 1? And if so, we've succeeded. On the thoughts about this code here, it is performant. It does really sort of what you would expect the computer to do to implement this test. But it's really hard to look at that and see what's going on. It's a lot more concerned with how to perform the query than it is with what is the query. And you've got to extract little bits of the query as you look over the code. So hard to read, easy to get lost in the plumbing. If you don't like writing your code that way, you might like to use visitors. The advantage that visitors have is they leave it to the API to do the work of the Instanceof and cast kinds of tests. And so this API has a accept method that takes in a visitor. The visitor wraps up some sort of query that we're going to perform. And there's a little more work on the API side to wire this up so that people can use it. One particular limitation is everything has to implement these accept methods, and then they all have to implement an interface. They've also got the same accessors as before. So the accept methods, are there to do the navigation of the tree, and the accessors are there to get to the data. And then, like I said, they both have to implement this interface in order for this to work. So if you work a little harder on the API side, then you can provide a visitor approach to accessing the data. There's more work to do on the user side because the user now needs to declare a class. Maybe it's an anonymous class, but there's a class somewhere that implements the visitor interface and that it provides all the code for the query. So here, as you can see, there's no more casts. That's maybe helpful. But we've split off pieces of our query into we've implemented this visitor interface, right? So there's two methods. There's the colored object method and the point method. Split up our algorithm into two different pieces. Because we're trying to make this convenient, it's a single object that can kind of handle everything. You might notice there's a bug here because that's the way it's been approached. If I have a colored object that contains another colored object, that contains a third colored object, all of those will keep recurring. And eventually, if we get to a point, this visitor will say, you succeeded, you found the thing that you were looking for, even though it's not quite the right shape. So it can be tricky with visitors to get the implementation right. And then finally, to actually use this thing, we need to create an instance of the visitor. You kind of want the visitor code to be right next to the application, or else there's different components of your program now. It's kind of a heavier weight thing, and you need to document what the components are for and how they work. So it's heavier weight, I think is fair to say. But it helps us to decompose the problem. A nice thing about this visitor code is that it forces the author to think about each case and write something for each case and make sure all the cases are handled. So that's the status quo as of JavaOne. As of Java 11, that's what you can do. What I want to talk about throughout the rest of this talk is these new features we've introduced with pattern matching and in the Amber project that makes interacting with data through, there's always a data API and then a consumer writing code. We want the code to be better, and we want to enable better APIs. For this first section, I'm going to be talking about APIs built out of record classes. And then towards the end, I'll come back to what about other kinds of APIs. Here's what we'd like to be able to write, and here's what you can write in Java 24. I want to this is just a high-level view, and I'm going to drill through a bit of each of the features that are involved here and some of the other features we've implemented. But as you can see, the entire API is just 2 lines. You've wrapped all your data in some record classes. We'll talk more about those. And the entire test is 3 lines. And it says basically what you're looking for. It's not preoccupied with how you're going to find the data or to perform this test. It describes the shape of the data that you want to find, and if that matches, then we succeeded our test. The intent is clear there. As a bonus, when you think about visitors, you've got an entire class and a hierarchy. If you want to change your algorithm, you've got to redeclare your class and try it again. Doing something like in JShell, where you're doing exploratory programming, you write 1 line at a time and kind of see what happens and then adjust your code. That's really hard to do. That's an advantage of that first example I had, where it's all very ad hoc and you can kind of piece it apart and see what you get. But patterns are even better for that, and it makes programming in JShell as an experimental, exploratory kind of thing super easy and convenient. And then if you're developing a test and you figure out exactly how you want to write your query when you're done, you can just copy and paste that code back into your permanent source code. Let's start with patterns. So everything through the rest of the talk is built on the concept of a pattern. Patterns, as I mentioned before, shift away from how to perform a test to what we want to look for. Patterns are always a combination of a test to perform and some variables to declare if the test succeeds. So there's always a true-false component of a pattern, and then in the true case, there are some variables that you get out of the pattern. It does the casting for you, it does the accesses for you, and it initializes the variables. You just provide the names, tell it what variables you need, and by performing the pattern test, you automatically get those variables available to you to write your code. So back in Java 16, we started with the first patterns in Java, and it was a very simple kind of pattern, just a type test. Patterns work, again, as the first step for where we introduce patterns in the language. They worked with Instanceof. So you're familiar with Instanceof being a object instance of type expression. And what that means is this object an instance of a class that is a subtype of the type I named? If it is, then the expression is true. If it's not, the expression is false. When you put a pattern in there instead of a type, what the pattern says is perform this test, and if it's true, also bind the variables in the pattern. And so the very simple type patterns that we started with are just variable declarations. String S, it looks just like a local variable or a parameter because it's really like in the grammar, it's the very same syntax. So I test against a variable declaration. If it is of the appropriate type, the pattern succeeds. The variable is bound to the variable. And then within that if, there's a variable S that I can work with. In Java 16, we introduced records, and then in 21, record patterns. So let me start with records. A record is a transparent data carrier. It's a kind of class. In a sense, it's just a class. But what is special about it is that there's no hidden state, there's no mutation, there's nothing encapsulated that is hidden from the users. It's all advertised within those parentheses in my record box here. That is what a box contains, an object and an int. And that declares fields of type object and int. It also declares a constructor with exactly that parameter list. It also declares the ability to perform a pattern, as we'll see in the next couple of lines. You can put things in between the brackets if you want to declare some additional methods, but the state is all captured in the header of the record. As Brian was talking about in the last talk, that's a limitation. There's a lot of limitations on what you can do with records, but by accepting those limitations, it provides a cleaner API because everybody understands how a record works. So given a record, in 21 we introduced record patterns. What a record pattern does, that's the thing after the instance of. If object instance of box, parentheses, and then some nested patterns in between the parentheses. The box part is just like a type pattern. It just says, is this an instance of a box? But then, rather than just binding a variable b to that box, we're going to access the components of the record and use each of those components to apply additional patterns. So in between the parentheses is actually a list of nested patterns. The first one you'll notice, string s, that is not the type of the component. The component is an object. That's not an error. What that means is get the object out of the box, and if the object is a string, then this pattern succeeds, and you can keep going. If the box contains some other object, then the test fails, and the entire pattern fails. So even on this pretty simple use of a record pattern, we're just decomposing the box into its two components. All the code below is implied. We're doing the instance of test and the casts. We're declaring variables. We're invoking accessors. That all gets collapsed down to just that simple line of code. And because the thing that is between the parentheses is also a pattern, you can do this multiple levels deep. You can have records inside of records inside of records, and a single line of code can dig into that object multiple layers deep and perform tests on the data. All right, so I've been talking about instance of. Patterns are also useful with switches, and so let me start with the earliest changes we made to switches back in 14. Switch statements have been in the language since the start. They're something that were inherited from C. They tend to be sort of optimized for low-level things like implementing parsers, that sort of thing. That one of the features of switches that most people who use them never liked is the idea that there's this block of code and there's different cases that jump you to different points in the code. And then you just keep running through the rest of the code. And the only way to end that is to put a break statement, or I guess a return, but you need to explicitly end the flow of the code, or it just keeps going and falls through all the other cases. That's rarely what you want. And so in 14, we introduced this arrow syntax as an alternative way to write a switch. It's the same idea. Take an input, compare it against multiple cases, and decide which one it applies to. But rather than just executing a block of code through the end of the switch, each case gets its own block to execute. We also added switch expressions. A statement is code that just has an effect. It just does something. An expression is code that produces a value. And so sometimes you want to take in an input, decide which case applies to that input, and produce an output. So there's sort of a mapping from an input to an output value. And switch expressions let you do that. And then you take the value and you can assign it to a variable, or you can do further computation with it. There's two different ways to write what the value of a certain case will be. You can just have an expression. That's what we do in the red and green case here. Or you can have a block of code. And if you have a block of code, you're back in listing statements. So in order to say, here's the value for this block, we added the yield keyword as a way to express that, sort of like a return, but for the switch. We also, when you think about mapping from an input to an output, unlike a switch statement, where you can just handle a few cases, a switch expression needs to be able to handle all the cases. And so there's a requirement that it be exhaustive. One way to do that is to use a default case. That's always possible. But it's also possible if you have an enum and there's only 5 cases. If you list all the 5 cases, the compiler recognizes that's exhaustive and doesn't make you add the default, which is nice because if you add a default, you're going to throw a this can never happen exception. And then somebody's going to be running the code in the future and say, why am I seeing a this can never happen exception? It's nice to leave that under the control of the language. I said patterns can work with switches. So in 21, we allowed patterns as a way to describe a case in a switch. So rather than just testing the input against 5 different values that it could be, you can test it against, in this case, 3 different patterns that could match. We also, in that first case, you see the when keyword. That's a special syntax for switches that says if this pattern matches also perform these additional side tests and don't match the case unless all the side tests work. So taking an integer, or I'm taking in an object. If it is an integer, and if it is equal to 42, then that's the first case. If not, we keep going and we look at the second pattern. The second pattern says, is it an integer at all? If it is, that case applies. And if we get down to the end and it's none of the above, then it's a default. We also added the null case for switches. So if, I think this went with the patterns. So if I have an input that is null, traditionally that would give me an exception. But sometimes you just want to treat the null as valid data and do something with it. So there's a case null. Sealed classes and interfaces are kind of a complement to records. You think about what a record does. It takes multiple pieces of data and aggregates it into one object. What a sealed class or interface does is it takes multiple variants and gives you a common supertype that consists of exactly one of those variants. If you look at the code here, there's not a lot that is different compared to how you would normally declare an interface that is implemented by some classes. But there's a sealed keyword that says it's a special kind of interface, and then there's a permits clause which explicitly lists the cases. So if I'm the owner of this API and I've explicitly listed those cases, I'm protected from somebody else coming in and providing their own implementation that isn't one of those cases. And if I'm a user of the API, I know any celestial object that I'm working with has to be exactly one of those three things. So if you're paying attention to switches, you might see where this is going. We can use sealed interfaces and classes in switches and do exhaustiveness testing. So if there's exactly 3 kinds of celestials and I have a switch, I can handle exactly those 3 kinds. And I've covered all the cases. I don't need a default again. One interesting thing to note is the compiler will still, it will tell you if you missed a case. If you got all the cases, it will still generate a default that throws a match exception. Why would that be useful? Well, because the class that you're operating on at runtime may not be identical to the class you're operating on at compile time. So maybe somebody added some new cases to the enum. Maybe there's a new variation of celestial that was added since you compiled. And so that provides a backstop. Again, it's just automatically, the compiler takes care of it and automatically generates that code. Unnamed variables and patterns, this is a simple thing. But sometimes when you're working with patterns, you just don't care what data is in a certain place. You don't need to bind a variable to a name. You just want to make sure it's the right type. So when you wanted to perform those sorts of tests, we introduced support for underscore as a special variable name that cannot be referenced. You can use it in the declaration. You can't ever refer to it later. And so that just signals the intent, I don't plan to use this variable. And it also works. We went through the language and found other places where we thought it would be appropriate. You can use that with exceptions if you want to catch an exception, and you don't need to do anything with the exception object. You can use it in lambda expressions if you need the shape of a lambda that takes in one input, but you don't want to do anything with that input. You can use an underscore. Finally, this is just a preview feature in 24, but everything I've talked about to this point has to do with reference types. Reference types have nice properties because they're all explicitly declared with hierarchies that say, I am a subclass of this thing, or I implement this particular interface. So all the classes and interfaces are in a nice graph in reference to each other. Primitives are in their own world, and we have conversions between them, but they're all very ad hoc, different rules for what kind of makes sense to get from one kind of primitive to another. Some of them are allowed in assignments, some of them have to be casts. So we asked the question, what would it look like to interact with primitives in a pattern? Does it make sense to say a double is an instance of int? you might just say, no, we're not going to, doubles and ints are different things. But we found that in certain cases, it can be useful to say, well, this is a 23.0 double. And I know that if I turn that into an int, it's still the number 23. I could even turn it back into a double again. It's still 23.0. So there's a relationship there that this preview feature captures to help work with different kinds of primitives. If you want to convert between different types, patterns allow that. You can perform tests on one kind of primitive to make sure it fits in another kind of primitive, and provide more flexibility for primitives. So I want to go back to this slide that I started with. You can see the records that appear in the API declaration. You can see type patterns and record patterns in this test, an instance of that's applying a pattern. And combining all these features together, we get the simple 3 lines of code that express the query that we're looking for. Here's a list of some future things. We're not done in this space yet. There'll be more preview features coming that'll turn into finalized features as we move forward. Some ideas that we've explored and we'll continue working on. Constant patterns are just a way to put rather than having a side condition that says x equals 1, just put the 1 right there inside the pattern. Var args and array patterns, some way to work with variable length lists of things where you don't know exactly how many components are there. Exceptions in switch. Sometimes a switch throws an exception when it is computing the input. And it could be useful to be able to handle the thrown exception as just another case. Patterns in for each, patterns in try catch. There's other places in the language where a pattern could make sense. Exception handling is really sort of the original pattern matching in the language. We're really doing things that are quite similar to what exceptions have done for a long time. And Brian, in the last talk, mentioned how Valhalla is working on non-nullable types. And if we have those, patterns could use those to give finer grained control over nulls. This is all speculative future things, but we're working on them. Finally, in this last section, I want to talk about what else we can do with the APIs. So I said declare records, and then records give you all this great stuff. What if you can't declare a record? So in this case, what if I have a point class, and what the point class models is clear. It's a pair of a couple of ints, but how I encode that inside the class isn't transparent. I've got some sort of data store underlying it, all sorts of different ways that you could actually encode this point, store it somewhere. But as far as the user is concerned, the user wants this to behave just like a record. It's just a bundle of a couple of ints. So first, let's think about how you construct this point. And notice that this part hasn't changed from when point was a record. There's a couple of inputs, and you aggregate those inputs into an output object. The object is a bundle of the pieces that were given. You could call it an embedding of those data points into an object. So what if I want to do pattern matching? What if I want to take that output and turn it back into its inputs? I can do that with records, as we saw. I can construct a record, and then I can use a pattern to deconstruct the record. What about for regular classes? If I have a colored point that consists of a point and a color, I've got all that data that I aggregated into P. Can I turn P back into all the data again? And this doesn't just apply to constructors, it can apply to methods as well. If you think about factory methods that take some input and produce an output that aggregates that data, it would make sense to disaggregate that data again. So there's a very general concept here about complementing construction and aggregation with deconstruction and disaggregation. What would that look like for our point class? At the use side, in the code that the user wrote, it's pretty clear. I'm going to take a point, and I just want to do what I did with records. Give me the x and the y within some parentheses, and I can work with them. How do I declare that in the class? Well, here's how that might work. It's the dual of a constructor, so we have a declaration that kind of looks like a constructor. It's only different because it has the pattern keyword in its declaration. And what that signals to the reader is, rather than constructing by taking some inputs and funneling that data into this, the object this, I'm going to take in a this, and I'm going to funnel data from this to the outputs, which are the parameters of the pattern declaration. I said we were embedding the data into the object before. Now we are projecting the data back out of the object. This is a really powerful concept, as I said. One thing you can think about is serialization, and there'll be a talk tomorrow from Victor Kling talking about data-oriented serialization that builds on this capability. So when you think about serializing an object, what you're doing is you're taking the object, you're decomposing it into some pieces of data that capture the essence of the object, send that data somewhere, eventually you'll read it back in and reconstruct the object again. So we got a disaggregation and we got an aggregation. That's the key operations that enable serialization. If you think about something like a conversion from a string to an int, we have an operation that constructs an int from a string. And then there's an operation to turn that int back into, or not an int, an integer. There's an operation to turn that integer object back into a string again. So those sorts of conversions between different objects could be expressed as an aggregation into some higher level thing and a disaggregation back into what you started with. Null checks are also an interesting piece of this. I haven't mentioned nulls much, but as you disaggregate in a pattern, if you encounter a null, when you invoke an accessor method, encountering a null gives you a null pointer exception. You tripped over a null here. So if nulls are allowed and you just need to steer around them, then you write a lot of complex code like on this slide to steer around the nulls. If you're using patterns, the patterns just say, if that's a null, well, that's a false pattern result. And so all those nulls multiple levels deep can be just handled as the case of this thing didn't match. So apply that concept to arbitrary classes that have these deconstructors, and you have a nice way to interact with nulls. Last thing I'll mention that we can do with these capabilities is sometimes you've got an object, an immutable object, and you want to turn it into something slightly different. There's a pattern of declaring an API where you've got to list all the different components and have wither methods. So what if we had wither expressions that do kind of similar to what I was talking about with serialization? They take as input an object, they disaggregate it for the class author, and then the class author can manipulate the data however they want. At the end, it gets aggregated again. So with those two tools, the ability to construct instances and the ability to deconstruct instances, the language can provide these sorts of capabilities to manipulate the data in between those two steps. So to summarize, we've added record classes, we've added sealed classes, we've added all sorts of varieties of different pattern matching capabilities. These all have to do with what we've been calling data-oriented programming, a focus on APIs that model data and users that just want to interact with the data. Not all code has that shape, but it's a pretty common component of most programs. You're going to have some of your code that's just modeling the data so that you can work with it. And we want to make operating on that data simpler and more convenient. There's a shift here from complex APIs that encapsulate all of the functionality that you might want when interacting with your data to simple APIs with simple accessors and deconstructors. And then it is the user code's responsibility to extract the data and use patterns as a convenient way to do that. All of this with This isn't a new language. It fits very, I think, nicely into the language that already existed. The Instanceof and the switch are still like the core entities that help you interact with patterns, and we've just let you put patterns in certain places where other things were allowed before. It's an evolution of those features rather than something completely different that you've got to switch your mindset for in order to operate on. There's some great progress here. I hope that all of these features in the aggregate, when you're working in Java 24, are a refreshing opportunity to program in Java over what you could do back in Java 11. And much more to come as we continue working. And that's all I have to say here, and I'm happy to take questions. Thanks.
So one of the things that you mentioned was the pattern matching with primitives, and one of the questions you asked is, do we consider a double to be an int? And your answer was yes in the case that it's like I have a 23.0. How do you determine when that 23.0, which may really be 23 and then a really small decimal, like there's 13 zeros and then a 2, how do you determine when that small decimal is the same thing as 0.0?
Okay. I believe the right answer is go look at the JEP for this feature.
Okay.
And it will lay out precisely how it works. But I believe it's down to the actual number that is represented. Every floating point number represents some real number on a real number line. And if that number is exactly an integer, then it works. And if it's not, it doesn't.
Okay.
So even if you're off by a tiny 0.0001, that's not considered an int.
Okay, thank you.
Another piece of that is if you can convert to your target primitive type and then convert back and get a different thing, then that is not a safe conversion for a pattern. Okay, thanks. Appreciate you being here. I encourage you to go get Java 24 and try these features out.